Welcome back, everyone. Now we are going to pay attention for the second speaker of this session, Hassan Rivaz from Concordia University. Hassan Rivaz received his bachelor from Sharif University of Technology and master from UBC, Vancouver, and PhD from Johns Hopkins University, USA. He's now an associate professor of Electrical and Computer Engineering Department and a Concordia University researcher in medical image analysis. He is an associate editor of IEEE TMI and IEEE TUFFC. He has served as an area chair for MICI since 2017. He's a member of organizing committee of IEEE IUS 2023 in Montreal, Canada, IEEE ISVI 2021 Nice, France, and IEEE EMBC 2020 Montreal, Canada. He co-organized the Curious MICI 2018 Challenge on correction of brain shift using ultrasound and Service MICI 2018 workshop on cerebral data visualization. He co-organizes advanced ultrasound imaging tutorial at IEEE ISVI 2019 in Venice, Italy, and 2018 in Washington, the US. And a workshop titled Machine Learning in Medical Ultrasound in ICIAR in 2019, Waterloo, Canada. He directs the Impact Lab image processing and characterization of tissue, and today he's going to give a speech on machine learning in medical ultrasound. So now we listen to his presentation. Thank you very much.
Hello, I would like to thank the organizers of the IPM 2020 for inviting me to this talk, and welcome to my virtual talk. So ultrasound is one of the most commonly used medical imaging modalities because it's real-time, it's inexpensive, it's safe, and it's portable. So basically, when you place the ultrasound probe on the tissue, it will give you a cross-section of the image right below the tissue. But it has much more potential with machine learning, and that's what we will be focusing on today. So to see why there's much more potential, first of all, we have to note that the original ultrasound signal is very, very complex and basically is not visually informative. So here we see the original ultrasound data in the left, and it's basically converted to these familiar B-mode ultrasound images in the right. But the issue is that most of the information in the raw data is basically discarded, is lost in this transformation. So basically, one of our goals will be to utilize this raw data directly using machine learning. Second point is that ultrasound has a very high frame rate. So here I'm showing two different movies of the tissue as it's deforming. In the left here, the deformations are much bigger, so they are very easily visible. In the right, this movie corresponds to shear wave elastography, and the deformations are very small. If you pay close attention, you will see some basically deformation in the tissue. Now, us as humans have evolved very well to see motion, but computational imaging techniques can better extract properties of the tissue from the motion patterns. And finally, even the B-mode ultrasound images are hard to interpret. So the image in the left is an ultrasound image of the brain. It's transcranial ultrasound, meaning that it's through the skull. So even if we show this image to even an experienced neuroradiologist, he or she will have difficulty interpreting this image. But once we show the corresponding MRI scan at the same location, the radiologist will be much better able to find correspondence between imaging features in the ultrasound image and the anatomy. So based on that, my talk will have two fronts. First, better use of raw frequency ultrasound data. And here we will discuss a variety of different topics. And then we will talk about how we can make even B-mode ultrasound easier to interpret. So let's start with elastography. So if we basically simply place the probe on the tissue and start deforming the tissue, these deformations can reveal mechanical properties of the tissue. So schematically, if we place the probe on the tissue and we start compressing the tissue as it's shown here, and we take two images before and after compression, we can compare these images and calculate the displacement image. And then from the displacement image, we can calculate the spatial derivative and get the basically strain image. Now, here in the strain image, if at some location the strain is low, it means that that part of the tissue is hard and it didn't deform. And that usually corresponds to pathological issues with the tissue, for example, cancer. Now, this is one type of elastography. There are many different types, but the idea is always the same. We have different images of the tissue as the tissue is undergoing deformation. And the goal is to calculate this basically deformation map, which is a very, very challenging task. So here I'm showing two different types of elastography, and we see two different types of motion. So here is quasi-static elastography. The deformations are typically much larger. Here it's plane wave imaging with basically for shear wave elastography. And here, instead of pushing the tissue with the ultrasound probe, we are creating the deformation with acoustic radiation force. So we basically formulated as energy minimization problem. So we say that we have a point here, X, which has moved to the new location, X plus D, and our goal is to find D. In order to do that, we formulate this cost function, which has a data term and a regularization term. Basically, the regularization term tells us that enforces some smoothness on basically the displacement field. Now, what happens is that C becomes a nonlinear cost function with more than 1 million variables often. And this is not easy to solve. So we have developed several techniques that solve this cost function, and the code associated with many of them are available online at sonography.ai. We have also provided a lot of ultrasound data, ultrasound raw data, both simulation and in vivo from human and animals. And you're welcome to use the data and basically and the code. Now, I don't want to focus on this in this talk. I want to focus on other topics. So basically, how to solve these cost function is will not be a topic of this this talk. Now, we proposed the first method to basically use optical flow neural networks for calculating the displacement field in elastography. This is our modified architecture where we use the raw RF data, ultrasound RF data, to basically estimate these deformation maps. Now, one issue is that when we use these computer vision optical flow networks, they use vision data, which is statistically very different compared to ultrasound data. So what we do is that we simulate ultrasound images with known displacements, and then we fine-tune these basically models using our simulated ultrasound images with displacement. Now, an issue with that is that, first of all, simulation is very simplistic. We cannot model nonlinear ultrasound wave propagation. We cannot model nonlinear tissue deformation. So those all create a domain shift between the simulation data and the real data that we collect from real tissue, from real ultrasound probe. In addition, there are many different imaging settings. For example, if you want to image thyroid, you have a different imaging setting compared to if you want to do transcranial brain imaging or if you want to image the brain. Again, we have different statistics of the image, which can also create domain shift and degrade the quality of the displacement estimation. Now, the things that we do have a lot of real ultrasound images from real tissue, but those images don't have any ground truth because in real life, we don't know what's the ground truth deformation of every pixel in an image. In fact, we don't know the ground truth deformation of any pixel in the image. So let's talk about the concept of semi-supervised learning. So in supervised learning, the word is very nice. We have a very large training set, and we can basically estimate the decision boundary nicely from this basically large training set. Now, assume that here in this new scenario, we only have basically ground truth labels of these samples, you know, in solid colors, and all of the other circles, we don't know their ground truth. You know, they are real data without known labels. Okay? Now, if we approach this problem again as a supervised learning problem, this is going to be the decision boundary that we are going to create. Now, in semi-supervised learning, what we try to do is we try to basically utilize these unlabeled data that come from real world to basically create better decision boundaries using the few known labels and many unknown labels. So based on that, very recently in MICAI 2020, we proposed a semi-supervised elastography method where we use pre-trained network in computer vision domain, and then we fine-tuned that network with real ultrasound images without ground truth. So basically, this is a flowchart of what we do. We have a lot of labeled data. We create a model based on that. We have a lot of unlabeled data, and we try to fine-tune this basically model using the real ultrasound images. Now, this is the architecture of our network, and this is our loss function. You're welcome to look at the paper, which will be published in the main MICAI conference this year. Now, let's talk about the second topic, which is quantitative ultrasound. Ultrasound is a fascinating medical imaging modality. It basically is created by from the interaction of the acoustic wave with many scatterers. And we can have different scenarios when we image real tissue. For example, we can have few scatterers that scatter ultrasound in different directions. These are resolution cells, so that's the minimum size that ultrasound can resolve based on its wavelength and other imaging parameters. We can have diffuse scattering, where we have a lot of small scatterers throughout the tissue, and different types. You know, so here, for example, we have specular reflectors. So this is when we have a strong boundary that reflects ultrasound, you know, in a certain direction. So these are big structures in the tissue. And these dots are small structures such as cells. So for example, this can be the border between two tissues, for example, the border of the kidney and the surrounding tissue. Now, what we want to do is we want to infer basically intrinsic properties of the tissue from the ultrasound image. For example, we want to find cell size, how many cells we have, per, let's say, cubic millimeter, scattering properties of those cells, and also attenuation of the tissue. So these are properties of the tissue. This is not intensity of the image, of the B-mode image that we show. And this will open a window into cell properties, which are much smaller than diffraction limit of ultrasound imaging. So here in the left, we have 3 cells that scatter ultrasound. What happens is that they are much smaller than the ultrasound wavelength, and the ultrasound image cannot basically resolve them. So going from these cells to this image, that's the ultrasound imaging system. And we get basically this. Now our goal is to solve the inverse problem and go from this image into this image where we can infer basically properties of the scattering medium, which is in this case tissue. So in collaboration with researchers in UNAM and Wisconsin-Madison, we basically proposed a novel quantitative ultrasound method that can basically extract intrinsic tissue properties. So here in this image, which is made from a phantom with known acoustic properties, we were able to extract the acoustic properties of the tissues, such as scattering and attenuation from the image. And then in other phantoms where these basically layers were invisible in the B-mode image. So here we can see that this phantom is made of 3 layers. In this image, it is again made of 3 layers, but the B-mode ultrasound image doesn't really show us. If you look very closely, you sort of see the boundary. So even in images where B-mode doesn't show us anything, we are able to basically differentiate these different layers because we use the raw data to find basically tissue properties. So here, the benefits of this quantitative ultrasound work is twofold. First of all, we use the raw data and therefore we can extract more property. Second, which is more important, is we extract intrinsic properties of the tissue. And we don't show a qualitative image that shows, brightness values at different locations. And these quantitative properties of the tissue can be very important biomarkers. So now let's talk about faster ultrasound acquisition. So in ultrasound, what we often do is that we focus the beam at a certain point so that we have a good resolution at that point. Now, what happens is that we have excellent resolution at the focal point, but away from the focal point, we have a very poor resolution. So here, for example, we will not be able to distinguish this square from this circle because the resolution is poor here. Now, the solution for that is that we can perform multi-focus ultrasound imaging. So we basically focus the image at different locations and then we average all of them into this image. What we get is excellent spatial resolution, but depending on how many focal points we have, our temporal resolution drops. So here we have 1, 2, 3, 4, 5. So our temporal resolution drops by a factor of 10. So here, if we were able to do, for example, 50 frames per second, in the final image, we are only able to do 10 frames per second, so 5 times slower. And it will also become susceptible to motion blur. So if, for example, we are imaging heart, which really deforms very fast, this averaging will not work because we will have motion blur. So we basically proposed a GAN technique to resolve this issue. But first, let's look at what is a GAN. So a GAN is basically a combination of 2 networks, a generator and a discriminator. which are fighting against each other. The generator tries to create data that looks real, and the discriminator tries to basically discriminate between the real data and the fake data. And these are both optimized concurrently to try to improve the both generator and discriminator. So we can look at these as criminals and cops. Right? So criminals are trying to generate fake money that looks real, and cops try to distinguish the fake money from good money. With time, criminals get better and cops also get better. So when this network is converged, the generator becomes so good that the discriminator cannot distinguish between fake images and real images. I should mention that this process, this training is very, very difficult, and it's not an easy task because this is a min-max optimization. So let's look at our setup. So this is an image where we have a single focus at 60 millimeters depth, right? And because our focal point is here, we see that, for example, this cyst at the top doesn't have a good contrast. Now, this is an image where we have 3 transmissions at 3 different locations, right? And we see clearly that the quality of the image is much better. So here I have zoomed in on around this cyst here at the top. So we see that when we don't focus on the cyst, the quality of the contrast of the cyst is quite low. Now our goal is to train again, which takes this image as the input and then generates an output image that looks like this, right? So the idea is to basically, instead of focusing at 3 different locations, only focus at 1 location, but create this image from this input. So we propose a conditional GAN framework in this paper, and we compared it to basically different CNNs, different super resolution CNNs, normal GAN, and our proposed boundary seeking GAN. And we showed that our results are much better. So this is in simulations. So these ultrasound images are simulated. We also tested it on real data. And we saw that, again, with our boundary seeking GAN technique, we can get basically quite nice contrast with this input image. Yeah, I like to here mention that most of the data, almost all of the data that I present in my work is available from basically sonography.ai website, and you're welcome to use the data. And if you want, you're welcome to collaborate with us on how to use the data. So the conclusion was that yes, we can actually get multi-focus quality ultrasound from single focus. So let's take let's basically stop this video and record the next of the talk in a second video. Hello, and welcome back to the rest of my talk. So now we will talk about aberration correction in transcranial ultrasound. So in ultrasound, we basically want to focus at a single point when we use conventional beamforming. So let me quickly. So here at the top, we sort of know the speed of sound in the tissue, and then when we fire different elements, we account for the different timing that it requires to reach a certain point, and then we can focus at that point. Now, the fact is that we assume a nominal speed of sound, which in real life will not be the same as the nominal speed that we assume. So here, for example, in the bottom, assume that we want to image transcranially. Now, the speed of sound in the skull is very different compared to other tissue, for example, brain or muscle. So what happens is that the beam doesn't focus at the point that we want to focus anymore. And because of that, the image quality significantly degrades. Now, we basically performed this simulation study where we apply aberrators to the transducer elements. So here, these are our weak aberrations and strong aberration profiles that we apply. So these are the time delays. And we see that when we have a weak aberration, we have some degradation of the quality of this target. When we have a strong aberration, we sort of completely remove that target. So we proposed a CNN technique to basically solve this inverse problem of going from a strong aberrated image to a nice and high contrast image. Now, this work has many applications in transcranial imaging when we want to look at the brain, but also in low intensity focused ultrasound for modulating brain function. Recently, there was a study that showed that low intensity focused ultrasound in fact improves the mood, right? Or it can improve memory or IQ. So there's a lot of interesting things to explore here. And also high intensity focused ultrasound for drug delivery and ablation. For example, we know that chemotherapy doesn't escape through the blood-brain barrier. And because of that, chemotherapy cannot be used for brain tumor. So one interesting application of HIFU for brain is to basically open the blood-brain barrier temporarily so that we can treat the tumor. And also in ablation, where we focus the beam at a high intensity so that we basically kill all of the tissue. All right. So now let's talk about image segmentation. So when we want to do image segmentation in clinical context, almost always we have to do transfer learning. Why is that? Because we have always few number of images. And basically annotating these images is a very expensive and time-consuming task. We have to ask experienced radiologists to do that, which are often quite busy. So we have few number of images with known labels. Now, classification is a very, very pioneering technique that has been extensively studied for transfer learning. And it has been shown in classification that when you basically classify a network for a certain task, for example, you basically classify this network to find cancer type A. Now, if you want to retrain it to also find cancer type 2 using the same images, it's basically better to fine tune the last fully connected layers. You don't touch these layers because you say that, oh, these extract the same features from the images. Now, in ultrasound image segmentation, we often transfer from other domains. For example, we fine tune the network on chest X-ray or MRI or other types of medical images or even computer vision images. And now we want to use them for ultrasound image segmentation. Now, the problem that we hypothesized is that speckle pattern is important in basically segmentation, in proper segmentation of ultrasound images. So, for example, if you work with an experienced radiologist, they will tell you that they look at the pattern of the speckle in the ultrasound image to find out the properties of the tissue. And this basically pattern, we hypothesize, we know that this pattern is extracted in the first layers. So we hypothesize that for, when you do fine tuning with ultrasound images, you don't have to, in fact, you shouldn't fine tune the last layers. The first layers are very important. So that was our hypothesis in this study, which is now in press in TUFFC. So here we looked at UNet for segmentation of ultrasound images. And we wanted to see the difference between shallow versus deep layers. Now, one confounding factor here is that because of these skip connections in UNet, the concept of shallow versus deep is not very well defined. So this basically, this layer, for example, can be considered deep because we have to go all the way here to reach it. But since we have a skip connection, this can also be considered as a shallow layer. Right? So in this paper, we did a very exhaustive study on different types of fine tuning. You know, we froze some layers and we fine tuned some other layers based on different definitions of shallow and deep, you know, by considering or not considering these skip connections. And we found out that shallow layers are actually important. So our hypothesis was correct. The speckle pattern in ultrasound is important for segmentation. And in fact, we found out that what is common in classification, and in fact, what many researchers have done in segmentation also following the classification work, where we fine-tune the last layer, often results in the worst results. Right? So it's very discouraged to fine-tune this last layer. So in fact, if we look at this as the contracting path of the unit and this as the expanding path, we found much better results when we fine-tune the contracting path. Or we can also look at this as an encoder and this as a decoder, and this is our bottleneck. So again, we found out that basically fine-tuning the encoder is usually better than the decoder. So these are some basically some results. So here, first row is first and second rows are simulation, and these are real ultrasound images from the tissue. This is our ground truth masks. This is the pre-trained model. And we see that the pre-trained model without fine-tuning works very poorly. So in this case, it doesn't segment any of them. Here also, it misses most of them. And even for the one that it finds, the dice ratio is quite low. For in vivo images also, it's not doing a good job. Now, we had a large database for fine-tuning. So we see that when we fine-tune the whole network, we get quite nice results, you know. So this is in fact quite similar to the ground truth. Now we basically looked at fine-tuning different parts, for example, contracting part, and we saw that you don't need to fine-tune the whole network. In fact, fine-tuning the contracting part gives you the same result as fine-tuning the whole network. We then froze the contracting part and fine-tuned the expanding part. Here, so expanding part is this part of the network. And here, again, we see that the performance is quite poor. Right? So basically, the first layers are the important ones. That's the lesson that we learned. And we did another study where we fine-tuned all of the network except for the bottleneck, block 5. Now, I have to mention that block 5 has many parameters. So this entire network has 30 million parameters, and the bottleneck itself has 15 million. So half of the parameters are here, half of the weights are here. And this row, this column and this column represent fine-tuning the same number of parameters, right? And we see a sharp contrast between these two columns. When we only train the bottleneck, we get horrible results. But when we train everything but the bottleneck, we see nice results. So this shows that this high-level representation of the data in the bottleneck is basically quite insensitive to changing the imaging domain from, you know, MRI to X-ray to ultrasound, which is a nice finding. All right. So still, segmentation of ultrasound images is a very difficult task, even for experienced radiologists. This is not an easy task. So here, what we tried to do was to basically do test time augmentation to find out the basically the accuracy of our segmentation, right? So here, what we did is that we shifted the image by different number of pixels in different directions. And then we also performed dropout during test time. Now, we said that our hypothesis was that if these segmentations and these detections that we perform are reliable, for example, during shifting, if we shift back basically the mask after shifting, we should always get to the same mask, you know? So this is sort of like using the data, the test time data, to find out the reliability of our segmentations. So when we are doing a good job, when we shift back, all of these detections shift back at the same location. But when the network is failing to detect or to segment, when we shift back, we basically come back at different locations, right? So here we see like very small variance in, you know, our detection. Here we see a large variance. So we said that, oh, if we see a small variance, it's reliable. And if it's a large variance, it's not reliable. And based on that, we were able to significantly improve the quality of segmentation in this paper, which is now on the in press. Oh, I should mention that all of the papers that I write here are available from my website, sonography.ai. Okay, so let's quickly talk about high dynamic range ultrasound before I talk about some of the clinical application of our work. So we are familiar with HDR when we have a scene with, you know, very bright regions and very dark regions. It's basically hard to show both of them, and because of that, we perform HDR tone mapping. So we applied this technique for the first time in ultrasound images. Again, we use the raw RF data, which does have these basically high dynamic information in it, but this information is lost when we perform traditional B-mode imaging. So we applied this to imaging the patellar tendon, and we applied it. We basically tested patients with tendinosis, which is a problem that happens when you know, you're in a basketball team or you're in a volleyball team and you jump a lot, or for whatever reason you're using your knee a lot and you get tendinosis. So we were able to see basically much better contrast in ultrasound images of the tendon. So now I'll talk about some of the applications of our work and specifically elastography. So first I'll talk about breast cancer related lymphedema. So lymphedema happens because we have localized fluid retention and tissue swelling caused by a compromised lymphatic system, right? And this is usually a side effect of cancer. For example, around 25% of breast cancer survivors will suffer from lymphedema. It's a debilitating condition. Some patients refer to it as even worse than the cancer itself because the hand gets so heavy and it can't move easily. And if it basically continues, you can have infections. So it's not it's a very difficult condition. And currently what clinicians do to basically to stage lymphedema is by the pitting test, where they basically press with the finger on the forearm to see basically the elasticity of the arm. You know, if it's elastic and it jumps back quickly, then you know, you're not suffering from lymphedema. But if the pimple returns after you remove your hand, then your arm is losing its elasticity and you're probably starting to get lymphedema. So this test is unfortunately very subjective, you know, and also we are only looking at the surface of the tissue. So ultrasound has been investigated to basically stage lymphedema, but it has been shown that it's not very effective. So we wanted to see whether we can use elastography. So we imaged patients, the left, and basically in breast cancer related lymphedema, whichever breast was treated during surgery or radiotherapy, the same arm develops lymphedema, right? So the patient has two arms, unaffected arm and affected arm. So we imaged them with ultrasound elastography, and we saw significant changes between the two arms in terms of basically elasticity of the tissue. We also have looked at tendon and ligament elastography for both knee and shoulder, and we got some nice results here. Now, one of our hypotheses was that if you have a tendon that's healthy and you pull it, you get basically uniform strain in your tendon. Now, if you have a partial tear that's microscopic and invisible in ultrasound, that tear will still generate stress concentration because it cannot bear any force anymore, or it can bear little force now. So basically, we can find these stress concentration and then relate it to partial tears, microscopic tears. So we noticed that from the ultrasound images, we found out that from ultrasound images, we can create these nice, basically strain maps in, for example, patellar tendon. And also in rotator cuff in the shoulder. So here again, we see that for healthy patients, we see this nice strain map in the rotator cuff tendon, RCT. So now let's talk about the second part of my talk, which is image registration to make ultrasound images easier to interpret. So now I'm going to show an image of brain shift. This was collected at the MNI, Montreal Neurological Institute. And I'm going to show an exposed brain. If you don't want to see an exposed brain of a person, you can basically close your eyes for a few seconds. So when the skull is removed during neurosurgery, the brain starts to swell out due to edema. And this swelling can be up to 4 centimeters. So we have a lot of deformation in the brain. Now, neurosurgeons use MRI images to basically guide them into finding out where the tissue is and where to perform the resection. And they have the neuronavigation system, which acts as a, sort of like a GPS. So like the neuronavigation system tells them where they are in real world, and the MRI image is sort of like the map of a city. Now, what happens after brain deformation is that this map of the city starts to deform. And if the map starts to deform, your tracking is basically useless now because the map is incorrect. To deal with that, surgeons often use ultrasound during neurosurgery because ultrasound shows the current state of the tissue, but MRI was collected before surgery and it cannot be easily done in the surgery. In fact, there are some intraoperative ultrasound scans, but doing surgery under MRI guidance is very expensive and also very, very time consuming. So if a normal surgery takes 1 hour, if you want to do it under MRI guidance, it can take 5 hours. And that basically increase in the time of surgery can cancel the benefit that you gain from more precise surgery, right? Because often longer surgeries are associated with more side effects and more issues. And since ultrasound is real time and portable, it can be easily used in the OR. So they simply roll an ultrasound machine into the operating room and they start using it during surgery. And the issue here is that ultrasound images are hard to interpret and they are noisy. But we have the preoperative MRI image. So our goal here is to deform the pre-op MRI to match the intraoperative MRI using the features in the ultrasound image. So The ultrasound probe is tracked in the OR, and several scans of the brain are collected before neurosurgery, during basically resection. So here, some part of the tumor is resected, and after resection. So they do this to make sure that they have basically removed all of the tumor and there is no residual tumor. I'd like to point out that in this paper, we have released a data set of ultrasound and MRI scans, many ultrasound scans and MRI scans of 23 patients. So it's a very complete data set, and I encourage you to use it. So we basically, in this work, we registered pre-resection ultrasound and post-resection ultrasound. Now, this is a difficult task because we have non-corresponding tissue. You know, some of the tumor has been removed in one of the volumes. And we saw that after we perform the registration, we get much better alignment between the images. We also performed post-resection ultrasound to MR registration. Now, this has a huge impact, because if you're able to do the registration of post-resection ultrasound to MRI, then you can look at the MRI and say, oh, it looks like I have some residual tumor here, so I need to resect more. And this is very important, because the resurgence of the cancer is a very important issue. If you have residual tumor, the cancer will come back. We also performed basically deforming the tractography images using ultrasound images. Now, our brain is full of wires inside, and when the surgeons do neurosurgery, the side effects are much smaller if they cut parallel to these fibers. If they cut perpendicular to these fibers, they will basically cut the communication between many different parts of the brain. And as a result, the patient suffers from many side effects. So it's important to try to cut parallel, as much as possible, parallel to these fibers, especially important fibers. But again, the issue is that once you do tractography in MRI, you open the skull of the patient, and then the brain starts to deform, and that tractography that you did before is invalid now. So in this work, we were the first to propose to basically deform these tractography images using intraoperative ultrasound. And we saw that we get basically much better results after basically image registration. So here, this is target registration error. We see large numbers in millimeter, but after registration, we can reduce these numbers by a very large margin. So there's a very bright future for ultrasound. So the image in the left is one of the early ultrasound machines. The probe was so heavy that the doctor couldn't hold the probe. A mechanical arm has to hold the probe. Now the probe is very light, you know, you can simply hold it in your hand. And also the ultrasound machine is in a cart, you know, you can move it in any room that you want. That's in sharp contrast to CT and MRI, which have their own rooms, and they are very sophisticated machines. So this makes ultrasound very easy to use. But future of ultrasound is even more accessible. So now there are ultrasound probes that are portable. So they wirelessly show the images on a smartphone, and they are battery operated. So the idea is doctors can carry these ultrasound probes like a stethoscope. You know, they can carry them in their pocket all the time with them. And because of that, you often see news about ultrasound in major news outlets, you know, new discoveries about ultrasound, and that make it easier to use. So because of this, I believe that there's a very bright future for ultrasound. So I like to talk about one clinical impact of our elastography code. Again, I like to highlight that many of the RF data, like raw ultrasound data, many images, and most of the code that I presented in this talk are available in my website at sonography.ai. So, for example, for our elastography work, researchers at University of Western Ontario, they applied it to prostate images. So here, this is a prostate image of a person who has prostate cancer. Now, their ultrasound machine allows real-time strain imaging. So this is the real-time strain image that they saw on the screen. And this image is quite noisy. It doesn't really show anything where the tumor is. So they used our elastography technique, which is dynamic programming and Kalman filter strain estimation. And this is the image that they generated. This image shows that there is a tumor here in this part of the prostate. Now, this person was, it was basically proved that this person has prostate cancer. So they removed the prostate completely. They did prostatectomy, and then they did histology of the prostate. So they cut the prostate and looked at it under microscope, and boom, they saw basically a tumor in the same location that the strain imaging technique had found. So I like to basically emphasize that it's important to release your basically code online so that others can apply to interesting things. For example, in this case, I couldn't have dreamed of such nice results. That they were smart. They applied it to a nice application. So with that, I'd like to thank the students in my lab, Impact Lab, who have done all of the work that they have presented, and also the sources of funding who have provided funding for my lab. And also I'd like to thank my collaborators who have been essential in the success of this lab. Thank you very much. And if you have any questions, feel free to contact me.
A very nice and informative talk. Now we are ready to take some question from the audience if there is any question.
Thank you, Mohammed, for the invitation. It was a pleasure to give a talk at the IPM Summer School. So I'm very happy to take questions, and thank for all the audience for listening.
Okay, thank you. It seems that here we have some questions. So the first question is that ultrasound also is used in industrial applications such as inspection. Can you retrain the model using non-medical ultrasound data and then fine-tune the model with the medical data?
That's a good question. We'll have to try. Unfortunately, in deep learning, a lot of things, you can't really tell beforehand. So often it's better to pre-train with another application than start from scratch, So it's probably useful to do that, but I'm not sure how useful, So I'm not sure, how much improvement we get by pre-training as opposed to just training from scratch.
Mm-hmm. Yes, I see. Well, there is another question. As far as I know, the generator network in GAN receives a prior probability as input to generate a fake image. Could you please give a brief explanation of what modification did you perform on the generator that it became able to receive an image to generate an improved version?
Oh, I see. Yeah, so I should have mentioned it. It's a conditional GAN. So it's not a regular GAN. So it's a conditional GAN, and it's conditioned on the input image. So we give it, you're right, usually GAN, gets a prior information and it generates some, fake image. Here, this is a conditional GAN that gets an image as an input and gives an image as an output.
Yes, thank you. And the next question is that as a local motion feature, except from optical flow, which others you have used in your research? What about 3D input data?
Oh, so let me see if I understand. So as the local motion features, except from optical flow, which others have you used in your research? So we basically used optical flow techniques for basically finding deformation between elastography, and in ultrasound elastography we can do three-dimensional ultrasound elastography as well. In fact, I did it during my PhD, so my input volume was a 3D volume, and my output, basically strain image, was also an output, was also a 3D elastography. Not sure if I answered the question, if I got the question. So let me know if you have follow-up questions.
Yes, sure. So another question is, you mentioned difference in different part of body tissue. What did you solve this problem?
Yeah, so here, so basically I can say that different tissues in the body have different properties. For example, if you want to image breast, or if you want to image the liver, first of all, the properties of those tissues are different. And second, in order to basically reach the interested organ, you have to penetrate different, layers of tissue. One very clear example is if you want to image the brain, right? So if you want to image the brain, you have to go through the skull, and it really aberrates the ultrasound, it attenuates ultrasound, and you basically have to, like, when you work with commercial ultrasound machines, you have to tell the ultrasound machine what organ you're imaging. You have to tell it, like, before you start imaging, you have to tell it that, oh, I'm imaging breast, I'm imaging, prostate, I'm imaging brain. And it basically changes presettings to optimize the basically image appearance for that tissue. So basically we sort of do the same, so in medical imaging, usually each organ has its own, body of research. You see, like a lot of literature on, prostate segmentation, and a lot of literature on, breast tumor segmentation, which may be using, similar techniques. But because of these challenges that I mentioned, often, you don't have a ring to rule them all. For every application, you need to, fine tune your technique and everything. So yeah, for different tissues, you need different techniques.
Okay, thank you. And the next question is that, can we improve damaged cell brain?
Oh, that's a good question. So I'm not, my biology and my medical knowledge is extremely limited, So like we all grew up in Iran, and in Iran, like if you go to math, you sort of ignore, all of the biology courses, which I regret now. So I have very limited knowledge, but there's a lot of interesting work now on, using ultrasound for different applications in the brain. So one application for modulating brain function, meaning that you basically excite or inhibit the basically different neurons, right? So this can be used for example, for treating depression. So there was a recent paper that came out that they showed that when you do like normal ultrasound imaging of the brain, this was a funny paper, you actually improve the mood of the person, right? So the person gets a better mood when you do like ultrasound imaging of the brain, because ultrasound like excites neurons and things like that. So that's application one, changing or modulating brain function. Application two is for, drug delivery in the brain. So like for any type of cancer, we can do chemotherapy, but for brain cancer, we can't do chemotherapy because of the blood-brain barrier, right? So the blood-brain barrier is like prevents big molecules from escaping, the blood into the brain tissue. So basically what we do with ultrasound is that we excite around the tumor so that we can disrupt the blood-brain barrier so that it opens, the gates open, and then the chemotherapy agent can go to the tumor, and it will be like targeted chemotherapy. So you only, you only target the tumor. and also for ablation, so you can actually increase the ultrasound volume, right, the amplitude of ultrasound, and then you can actually ablate or like kill all of the cancer cells with ultrasound itself. Now so basically these are different applications that we can do to like change the brain function with ultrasound. Now, if by damage you mean cancer, yes, there's a lot of work to treat cancer with ultrasound. But like if it's a dead cell you want to treat it with ultrasound, I'm not sure. Maybe it's possible.
Okay. Yes. Thank you. And the next question is that fixing strong aberration to reference is something like increasing the contrast light. Right. How can the network solve for the speed difference of sound in different tissues and do such a thing? Does it combine multi-angle views, something like CT, to produce a density map?
I see. Yeah, that's a good question. So so basically what we do in ultrasound is that we try to focus at a point, and then we basically, so we have a lot of so if I use basically this remote as an ultrasound, so we have a lot of basically small ultrasound crystals at the bottom of this thing, and with each one of them we receive one RF signal, right? So what we do is sort of like in fact it's quite similar to ultrasound elastography and motion estimation. So what aberration, so you can either have motion in the tissue. When the tissue deforms, you have real motion in the tissue, but you also can have apparent motion in the tissue. What's apparent motion in the tissue? That's created because the speed of sound is different, right? So remember, the image that we generate is all based on sound traveling to the tissue, right? So for example, if the sound speed increases, you think that the tissue is shrinking because it's now taking smaller time to reach the probe, right? For example, we use this for imaging, for temperature imaging, right? So like as the temperature of the tissue increases, the speed of sound also increases, and it looks like that the tissue is shrinking. So you can link the shrinkage to the temperature change, right? So it's the exact same phenomenon in aberration correction, right? So changes in speed of sound create some, sort of motions in the tissue, and then you can estimate those motions to basically correct for them. And there is now a new paper. In fact, we were working on this also, but we were scooped by a group from MIT. So they recently, this paper is still in press. So they use deep learning to estimate speed of sound from ultrasound. So it's not like CT, it's not multi-angle. What you get is basically a lot of readings from many crystals on the probe. That's okay. A good question.
Yes, thank you. And the next one, is there any treatment for CP children?
Any treatment for CP children? What is CP? I'm not sure what CP means.
Yes, can you please clarify, Mrs. Razia? Okay, she's writing.
Yeah, she's typing. So, Mohammed, this is the 4th IPM summer school?
Yes.
Yeah?
Yes.
Oh.
Oh. Something
yeah.
Yeah.
And the previous summer schools, I assume, were not virtual, were they?
Well, I do not know exactly, because this is the first time I'm participating in this summer school. Yes. Yes. Okay, for CP, they mean children who their cells are so weak. So is there the treatment for them? And they cannot speak.
So CP, what does CP refer to?
Yes, the exact term, if you...
Oh, children whose cells are so weak.
Mm-hmm.
I don't know. Honestly, I have no idea.
Okay. So if you can please give us more information in your question, we would be very grateful. And Okay, the previous one were not hold virtual, so it was the real one with coffee break and the nice things. Okay, another question here is a cerebral palsy CP is a group of these. This is the explanation of the previous one. CP is a group of disorders that affect the person's ability to move and maintain balance and posture.
I see.
So is there any treatment for this?
Yeah, that's a good question. So if it's, I don't know what causes cerebral palsy, if it's related to the cerebellum, to the brain, then right now there is a lot of push in ultrasound to basically treat different, brain issues using focused ultrasound, right? So basically the nice thing about ultrasound is that you can focus it at any point that you want. So if it's caused by, some issues in the brain, then it's possible to, at least, look into this. But I haven't seen any paper that, tries to basically treat cerebral palsy with ultrasound.
Okay, thank you. So is there any other question here?
Yeah, I see one from Babak. He's asking, you also said ultrasound simulations are not accurate. Why? Doesn't it have a solid physical background? Yeah, so, ultrasound simulations only simulate linear acoustics, and nonlinear acoustics is very important. In fact, we use nonlinear acoustics for some applications. So that's one, that's one limitation of basically simulations. That's the one I can think of, but I'm sure there is many more, so yeah, any simulation has some, has some basically limitations.
Okay, thank you. So if there is no other question, I have a set of questions here myself. And in your research, do you face with data imbalance in your experiments, basically?
Yes, yeah, we often do. That's a good question. So, most people are healthy, right?
Yes.
So a lot of times, the classifier can be biased into thinking that, everybody's healthy. So yes, we have to deal with that.
Okay, what is your primary approach to deal with this problem? Do you use sampling or other techniques?
Yeah, so we basically use, we change the, the cost function, to something funny is happening. Did you, was I muted or?
No, we can hear you.
Okay, all right. So yeah, we basically use, the common techniques when we have imbalanced data, so we either, we do bootstrapping, to sample more from, the small data set, or we basically weight the cost function, we give a higher weight to the smaller, smaller class. There's also, this focal loss that, that was used for detection. And again, it's instead of simply, weighting the cost, it also, adds some other terms to the loss function to basically specifically deal with the data imbalance. Okay. Yeah, so we always deal with that. Yeah, in fact, I don't know if you guys know Nasir Nawab. In fact, he's a great, person you can ask next year to give a talk. He's one of the top researchers in, in the medical imaging field. So he has this nice paper, like few nice papers, where he is basically trying to model anomalies as, errors in reconstruction, because like here, his argument is that, there are many different types of cancer. We can never, like our classifier can never ever see all different types of disease. you know. So what he tries to do is that he tries to reconstruct, like he tries to reconstruct basically the image using, let's say, an autoencoder, and then the error that he gets from the difference of the autoencoder and the normal image, and this basic test image shows what regions of the image are, you know, not abnormal, right? So yeah, so you can do tricks also like that when you have, you know, many different types of disease and some of them are very rare, you know, you can never get enough samples.
Yes, yes. So given that some anomaly detection algorithm can be applied in this topic, do you think that some other saliency detection methods can also be applicable in tissue damage detection?
Yeah. In fact, you know, this is a very good time to do research in this field, you know. So there's many great ideas, you know, you're mentioning so many of them. So yes, that's also a good idea.
Okay. And how about the validating the generalization of the learned representation? Have you done any experiment using in the cross dataset setting that you learn some representation on one data and apply it in the real world or other datasets? How much performance drop do you get?
Yeah, so it depends, you know, depends on different applications. That's a good question. So in fact, we have one paper right now under preparation. We haven't submitted it yet, but you know, we were very surprised. So this paper is a quantitative ultrasound paper. So we basically use ultrasound, quantitative ultrasound and deep learning to find the concentration of scatterers, right? So scatterers are, like, as you remember from my talk, they are smaller than the ultrasound wavelength. So there's no way to actually see them. But basically we can get their statistical properties from ultrasound, right? So we trained basically a model using simulation, and then we fine-tuned it on a lot of phantom data that we collected, and then we tested it on real breast data that like we never trained on or anything like that, and it was doing a decent job, you know. So it was basically able to find quantitative ultrasound properties of the breast without seeing any breast data before, and like we were very surprised.
Yeah, this is very amazing that, because this is a serious problem in many theoretical issues, that sometimes we train a very wonderful model on some data and we cannot apply it on other tasks. In my own research, I have the same problem and try to solve it in the PhD thesis. Okay, thank you very much. So it seems that there is no other question. So I again want to thank you for your wonderful talk, and it was very informative. And I want to wish you a very lovely and wonderful Sunday.
Thank you. Yeah, thank you very much for the invitation. You know, I was very, you know, impressed by the questions. And I think, by the way, I don't know if you played the 3 videos that I provided you with, or maybe you only stopped at the second one. So in the third one, I provide, you know, some with some, you know, links to some of the databases that we provide, you know. So in fact, you don't need to play the video, but if you guys go to data.sonography.ai, you see a lot of, you know, data from, you know, phantoms and you know, some patient data. And also if you go to code.sonography.ai, you see a lot of code that we provide. And also if you guys, you know, want some data with our ultrasound machines, we will be very happy to collect them. Right now, it's the university is closed because of COVID, so we can't collect any data now. But in the future, I will be very happy, you know, to help out and, you know, collect some data. So, and if any of the audience for your research, you know, you're facing some difficulty, or you think that, oh, if I had this piece of equipment, that would have been great, let us know. We will be happy if we can help.
Okay, thank you very much. That's very useful.
Yeah, sure.
Thank you, and have a very nice day.
Thank you. You too. Bye.
Thanks. Bye. So now we will have a short break, and we will look back for the last talk of the day, which is gonna be at 6 p.m. Tehran time. So we'll back sharp. Thank you very much.